Hi, I'm James Wahlberg, and I'm going to talk to you about how to calculate how much material gets deposited on or removed from an electrode in an electrochemical reaction. A lot of times there are solids produced or consumed or gases produced in electrochemical reactions, and we're often asked to calculate exactly how much material is either produced or consumed. So in this video, I'll show you exactly how to do that. Let's go. Now, the reason that we would even care about knowing how to do this is that electrochemical systems are often used in purification processes, either in the laboratory or in industry. So we often would see a mixture of metals being purified through electrolysis, or gases being produced, again, from a mixture or even from ions in solution. So the way to do this is to, first of all, make sure that we're beginning with a balanced reaction. Just like everything in chemistry, it's always about the number of moles that react with each other and the number of moles of product that are produced. So let's make sure that it's balanced, first of all. The next thing we'll have to do is calculate how much charge is involved. So we'll be putting in some current, and of course current, represented by I, or amperes, is the amount of charge in coulombs divided by the amount of time over which those coulombs move past a point. So we'll have to solve this equation for Q, the amount of charge that we're actually talking about. Once we have that amount of charge, we'll divide that number of coulombs by Faraday's constant, which is here on the screen. It's 96,485 coulombs per mole. So that means if we had 96,485 coulombs of electrons moving, we would have 1 mole of electrons. So what we're really doing is taking the amount of charge and converting that into a number of moles of electrons. Now, once we have that number of moles of electrons, we can use that number of moles to look at the balanced reaction and see how many stoichiometric equivalents of electrons were used. And I'll show you exactly what that means as we look at a couple of examples. But basically here again, we're looking for the ratios in terms of moles of products and reactants. Finally, we'll use that molar ratio to then calculate the number of moles of product that are actually produced. And then if we're trying to calculate mass in grams, we'll have to convert the moles of product into mass in grams. Or if we've been asked to calculate a volume of gas produced, we'll take that number of moles of gas produced and use the conversion factor of 22.4 liters per mole of a gas at standard temperature and pressure. So that sounds like a lot of steps. But let's walk through a couple examples, and I think you'll see that just following the logic of what's going on, this really isn't too hard to do. So let's start here. In example A, we're told that in an industrial process that produces chlorine gas and pure metal sodium from the electrolysis of sodium chloride, we're going to consume 4 amps of current for 1 hour. So we need to find out, under that set of conditions, how much solid sodium metal is produced. All right, so let's start with the balanced reaction. So there it is, we've got molten sodium chloride. So we have sodium ions and chloride ions giving us solid sodium and chlorine gas. But look at that, the chlorine is actually a diatomic molecule. So in order to balance this, we're going to have to put 2's across the board here. And now we have a balanced equation, so now we can start. All right, well, let's see how much charge is actually involved. We have a 4 amp current applied for 1 hour, and 1 hour, of course, is 3,600 seconds. So if we do that conversion, we see that this amount of current over that time is 1.44 times 10 to the 4th coulombs. Okay, so we'll take that number of coulombs, 1.44 times 10 to the 4th, and now we'll use Faraday's constant to figure out how many moles of electrons that is. Remember, Faraday's constant is 96,500 and change coulombs per mole of electrons. So if we divide the number of coulombs that we have by that number, we see that that number of coulombs of electrons is actually 1.49 times 10 to the minus 1 moles, or just a little more than 1/10 of a mole of electrons. So that's how many electrons we have to work with. Okay, now going back to our reaction, we see that while there are 2 electrons consumed for every 2 moles of solid sodium that are produced, that's the same as saying 1 to 1, because we can divide both the number of sodium ions, 2, and the number of sodium metallic atoms by 2 and have that same ratio. So the molar ratio here, even though in the balanced equation is 2 for 2, the molar ratio is really 1 for 1 in the simplest form. So therefore, we know that for every 1 mole of electrons, we will get 1 mole of solid sodium produced. Looking up the atomic weight of sodium, which is 23 grams per mole, and then applying that to the number of moles that we're actually able to produce, we find that over that time, with that current, we'll produce 3.47 grams of solid sodium metal. So let's look at that same system, but now look at the other side of it, the other electrode, at which we're producing chlorine gas. And we need to know how many liters of chlorine gas we're going to produce under those exact same conditions. Well, we'll have the same reaction, but notice what has to happen here. In order to produce 1 mole of chlorine gas, that's diatomic chlorine, Cl2, in order to produce that, we're actually going to have to consume 2 moles of electrons, because the stoichiometry there is 2 to 1. You can see that for every 1 chloride ion, we're going to have to remove or oxidize away 1 electron, but we're going to have to do that twice. We're going to have to oxidize 2 chloride ions in order to get 1 mole of chlorine gas, or rather 1 molecule of chlorine gas. So there's a different molar ratio here, because we still are applying 4 amps over 1 hour. So we produce 1.49 times 10 to the minus 1 moles of electrons. But as we just saw from the molar ratio in the equation, it's going to take 2 moles of electrons to produce 1 mole of the chlorine gas. So therefore, with that number of electrons, we will actually produce 7.45 times 10 to the minus 2 moles of chlorine gas. So that's how many moles of gas, but we're being asked to tell how many liters of gas will be produced. To find that, of course, we will take that number of moles of gas, multiply it by our conversion factor of 22.4 liters per mole, and we see that we will produce 1.67 liters of chlorine gas. So again, it seems like there's a lot of steps in this process, but if you just think step by step what we have to convert, see how many electrons are needed, and then solve for what you're being asked to solve, in a little practice, I think this will go just fine for you. All right, thanks for watching, and good luck with your chemistry.